So I don't know if you can see it, right, but there's goes down 2 levels, right? So you got the fingers coming out there. Manufacturing those fingers in the middle on the next layers down, because this is already 3 via structures, doesn't yield that well all the time. Now they can yield it the final yield, but it's because they go back and people sit there with microscopes and hand touch up all of the fingers, every single one of them.
Hello, everybody, and welcome to the OnTrack podcast. I am Zach Peterson. I am your host, and today I am talking with Sean Patterson from Nano. He is Chief Revenue Officer and President of Americas, and today we're going to be talking to him in his new office in Massachusetts. Sean, thank you so much for joining us, and I see you have a very open office concept.
We're bringing a new concept to the world. It's the ultra open office concept.
Yeah, when I was talking to someone from Nano and they said you guys had a new office, you normally don't expect it to be totally open like that, but wow, it really is new.
We're startup, right, and trying to move the speed. So we got the keys last week, and if I sit here for another 2 hours, one of our first machines is arriving and go right where I'm sitting.
Oh, wow.
And yeah, so we just got about 25,000 square feet in Waltham, Boston. Waltham, Massachusetts, just outside of Boston.
That's excellent. You guys are moving
Yeah.
up in the world.
Yeah. So we just got the keys, and now it's about filling it up. But we're trying to move with speed, right? So it's not like some big ribbon coming. We'll make a beautiful office and then cut the ribbon and we open it up. It's about going and keeping up. So
Sounds like the company has been growing quite a bit recently then, if you guys have to move into a new facility.
for sure, and I think the United States. I started in July last year. About 5 people. We're about 39 now here, and still continuing to grow. It's more of a limitation of how fast we can hire and find the right skill sets. And anybody listening, please check out at nano-gi.com. We have plenty of roles posted for those interested, especially on the application engineering side for digital application engineers. That's where we're here and ready to keep going. Globally, we went from about 60 in January of last year. We're over 500 now. About 300 of those
Wow.
are in Israel. And that's both
excellent.
organic and NMA as well.
Yeah, that's excellent. Well, for those in the audience who are not familiar with Nano, Nano is a additive manufacturing company specifically for circuit boards. And when I was originally introduced to Nano, back when I think one of the original founders was still running the company, it was a big shift in mindset for me to think about 3D printing being applied to the entire circuit board. Because these days we talk a bit about additive processes, and it's more for fabrication and on the traces, getting copper conductors down all the way to very small feature sizes. But you guys are literally printing everything.
hmm We are, we're the only multi-material, and I'll say by definition, therefore multi-layer 3D printing option for electronics out there. And I think even the industry is, I think, sort of improperly using printed electronics because it's about that's usually attached to metallization on the outside of things. And we have, competitors, for lack of a better word, that do those kind of things. That's not really where our focus is. Our focus is to make, circuit boards out of thin air. And there's a completely functional one. And as I often like to tell people, certainly my sales team is, while the easy elevator pitch is we make a 3D printing circuit board machine, it's actually kind of shoots you in the foot because it's more than that. So yeah, can we print a 10-layer Kroger file? Yes, but that's not the point. The point is that it's electromechanical structures, right? And so here's a drone printed from nothing. Sure, the arms are dielectrics, and we'll work on more material strengths. But this is, and the motor stators are up there. That's why you see those coils on the edge there. We have a larger version that runs at 2,300 RPM. But even at that, you look on the edge, and there's topography to the center of that, right there, sticks up in the
Yeah.
middle. Okay. And so that's why it's more about structures, and we have to like advance our minds. It's not any layer board, it's any structure board, and so that's why I say it's a bad elevator pitch, because it ties people mentally back to a 2D, 2.5D, if you consider vias, mindset, which is where the world's at. And And so that's why it's a bad pitch, but it makes a mental connection of, okay, they're printing electronics, but it's structures really.
Yeah, and I think when a lot of people who may not have been involved with 3D printing or more advanced 3D printing processes hear the term 3D printing, they're probably still thinking like fuse deposition, where you basically have the filament and then it's going through the aperture and then it's, the
Right.
head's moving around and printing like that. And so I think it's a bit of a mental leap to try and imagine, well, how do I apply that to a circuit board? Are you now
Hmm.
just, doing the same thing but with conductors and dielectrics?
Yeah. Um, yeah, I like to compare the like I'm going to go the legacy 3D printing, which is metals and plastics, right? And that was a evolution of manufacturing. Okay, people humans, think in a 3D mechanical space, right? All of us, whether you're a mechanical engineer or not, everyone does. 5-year-old playing with Legos, right? Manipulation. I understand this stuff now. Sure, yes, some of us go to MechE and study in college and you get statics, dynamics, etc. Um, and you go to a company and now you're still designs. Your designs aren't related by creativity. In many ways, like artist sculptures are mechanical engineering, right? It's these 3D structures. Um, However, what 3D printing brought was, I use the classical example of, if I design as an engineer a hollow sphere. 30 years ago, the manufacturer say, we can do it for you. It's going to be two halves and we're going to weld it together. And here's your hollow sphere. 3D printing comes along mechanically, and it now says, okay, I can actually do it in one shot now. And yes, it does change some DFM, and people can get more creative, but it doesn't necessarily change the ideas of those mechanical engineers. Um, and with electronics, it's totally different, right? For those that are, I'll say, crazy enough to be a double E in college, maybe they don't ask for much hurt as a chemie, but still, you're going. You don't really think about electronics in a meaningful way or understand electronics in a meaningful way until you're in college. And I'm sure there's some wonderful high schools that can get people there, but it's a totally different spectrum. And it's electronics is it's the conductive and the dielectrics, right? Um, and so when you show up for day one of your double E classes, you get a 2D piece of software that's handed to you, right? ECAD is 2D. And so people don't naturally think in the 3D spectrum because they're never ever taught to even think that way. I mean, certainly some RF designers and things like that HFS, things like that. And at the end of the day, you actually collapse it down to get into a PCB production and you flatten out your 3D design. But most electrical engineers are operating in an ECAD software. And so people just never naturally think that way, one. Then you go to industry, and you're still using the same piece of ECAD. And so, where many years ago, most companies, most OEMs used to manufacture circuit boards in house. Some of them still have PCBA, but most of them have generally gone out to contract manufacturing. So now you have contract manufacturers that are now sort of removed from a direct OEM influence because you're trying to support all these OEMs. And so, if there's no demand for 3D structures, they're only going to have the interpretation of ECAD, and they only have equipment that supports 2D structures. And so there's this sort of vicious cycle that sort of doesn't allow us to think in a 3D spectrum, let alone it's much harder to think about electromagnetic spectrums in a 3D sense. And then add on top of that, the standards that have really developed for electronics, which are one of the oldest consortiums ever founded by engineers for standards, that have evolved for right reasons, for reliability and all these things. And now you have an entire industry that's sort of hard to change. And so when we think about 3D mechanical printing, it was this evolution of manufacturing. It doesn't change the world. It doesn't change the designers and all those kind of things. Electronics is a revolution of the entire system, and it starts with education at the universities, which is fundamentally why we have this wonderful new open office concept in the heart of Boston, because that's the densest population of schools that you can find mostly in the world, right? And so we need to go back to there, no different than Apple did when the original Apple 2Gs or whatever came out, and you gave it to all the elementary schools and things like that. So that's this fundamental difference, I think, between the two, and a much tougher. And so, coming back to your total question here, is we're putting two materials down, and it's different than even mechanical printers that put two materials down. We're putting them down because one's a dielectric and one's a conductor, and they have a functional role to play. but also when you're putting them down layer by layer by layer, and I'm not talking about PCB layers, I'm talking about granular levels of layers of a 3D printing. Um, as you're curing, as you're sintering, the CTEs and the properties have to play nice as that's happening on each layer, and then the whole structure then has to operate onto these standards and rely that the world is expecting. So it's a more difficult problem to solve, and you can't just throw any material set out there. Much would you see that's ubiquitous in the 3D printing market, and it's sort of a very open landscape of companies out there, because all you really need to do is make a deposition method through an FDM, and then you can use any plastic you want that goes through that same mechanism. And it's different for us. While we work with customers that want to try new materials, they can't just go and throw that material in our machine and hope that it just comes out, because it's about the interaction while you're building it and then total thing at the end.
Yeah, I was going to ask about the materials, but you actually brought up something really interesting about the drivers of advancements in manufacturing and then taking that back into CAD. We were talking to another manufacturer here just recently from Sierra Circuits, and he kind of said the same thing, that, customers aren't demanding enough of their fabricators to then push the fabricators to demand more from the manufacturers of the equipment. And so we shouldn't be surprised that we get stuck in this kind of 2D planar landscape for manufacturing PCBs.
Yeah. The semiconductor industry has a much easier time with this. It's a much tighter controlled supply chain, but also semiconductors are generally making a product, right? Now, multiple product lines, I get it, but how many different, pick your processor du jour, that processor goes on how many different circuit boards? Right. It's circuit boards are contract manufacturing for every single design, right? And even you can even buy the same motherboard and you don't even know the rev spinning behind the scenes, and the process is the same, but the designs are changing in this PCB itself. And so there isn't the education, there hasn't been the software. We have a software system that we are in alpha and beta phases with right now, that really translates ECAD into MCAD. Now you can design in both areas, but we're working on bleeding the two together and really driving the engineering together between electrical engineers and mechanical engineers and so electromechanical engineers, to think about different ways to solve things. Again, I showed the drone, right? Okay, so now you have an electromechanical structure that's functionally mechanically and electrically to solve a problem. But yeah, so anyways, the circuit board industry just doesn't have that demand. Look, circuit board plants are not putting $20 billion fabs into Ohio. Okay, this most, especially in the U.S., really went through mom and pop shops, and then there was this kind of build up, and then offshoring that happened in the sort of 90s and 2000s. I mean, you go back in 2000, 3,000 circuit board shops. Now there's less than 300, and they either went by the wayside. So they don't have the capital to really try new things. I worked for TTM Technologies before, 2 jobs ago, running most of their North American operations, and they were the few that we could actually get to even considering futuristic R&D that's at the manufacturing level. And there's very few OEMs that can drive fundamental changes that require hundreds of $millions in capital recapitalization. Apple being one of them, right? And pushing MSAP, right? MSAP's really here now because of that. Right. It was experiments, but now you actually have a demand. But it came from that one OEM. And it caused all those plants, their suppliers, to recapitalize hundreds of $millions to do that. And so you have to have the OEMs doing that. And there's very few places where that happens. And that, by the way, is high volume, low mix. And most of the stuff in the US is the other way, right? Right.
Well, and then
high mix, low volume.
When Apple is demanding something like that, people have a real incentive to invest, because they know, like, oh, it's Apple. They're going to be putting this into 100 million units a year, right? More than that a year. Right. And so, of course, it's going to be low risk. So it's worth the investment, I think. Going to, shift in the planar process and trying to innovate there is suddenly very high risk for a number of reasons. But you brought up the fact that at least the American cohort of manufacturers, the number has gone down, and I think a lot of them are still small shops. So where are they going to get the money?
Yeah, there's don't quote me on this, but I think there's only three companies over $100 million of bare board, right? And so again, a same a Summit and a TTM. I think
Yeah,
Amphenol is just below that,
that was
under
Summit.
100 million.
Summit what came to
But if you
mind.
really look at it, it's right,
Yeah.
and Summit's really come via acquisition very quickly in the last few years, and so it's not really like you're building that. But that's the way TTM evolved as well. And
Hmm.
nobody's really, except for like Wheelan and Green Source, put, and there's a few other projects out there to actually build, greenfield plants. But we have to figure out how to really engineer those facilities to not take all the manual labor. But when you're in this high mix, low volume world, there is a lot of touch labor. I mean, when I was a GM in Stafford, Connecticut for TTM, right? That's the largest A&D plant in the U.S. And I'm just, again, don't quote me on the total numbers, but something like 20% of the operators were like hand touch operators, because when you start trying to do, let me see, like structures, like even just flip chips, right, in a high mix low volume world, right? And so I don't know if you can see it, right, but there's goes
Hmm.
down two levels, right? So you got the fingers coming out there. Manufacturing those fingers in the middle on the next layers down, because this is already three via structures, doesn't yield that well all the time. Now they can yield it the final yield, but it's because they go back and people sit there with microscopes and hand touch up all of the fingers, every single one of them.
They're
And
going through
and
with
I
a,
think
like
a
a
lot of those
focused eye.
things are
They're going through with like a focused ion beam to do that.
no, usually with knives. If it was that way. But now you're asking for, right? But the industry's also kind of created this in some way, because the PCBs, people get in arguments with me about this all the time, but it's contract manufacturing. It's treated price wise as a commodity. And we can argue about whether it's a commodity because you can go to anybody to get it done, but look at the yields behind the scenes and see what's really happening. But I say it's not a commodity because every single one is different, and the yields are different, and it's not just this thing you can buy off the shelf, but it gets priced that way. And so to get those huge recapitalizations, it costs a lot of money. I mean, you see, these iterations of PCB plants out there. There's like solid numbers of revenue for PCB plants, from like 2, 4, 8. You get to a 20, 40, 80 million, 120 million. If you're in the middle there on a revenue, you're not utilizing all the you're either like overbooked or you're not utilizing all of your equipment, and you can't stay in the middle there because you have to wind up adding an entire all these areas that are your Herbies if you've read about constraint theory. But you have to be able to run these things in parallel because the throughput. And then you get more complex, especially again low mix high volume, where you got via structures left and right. One thing's going through as a straight through hole, maybe the next one's with through hole with the back drill, but then you got other ones with any layer going round and round and round in the PCB shops while other things are trying to go through, and it's very very difficult. It adds the like is a very complex manufacturing process because of that.
Yeah,
It's just the complexity of everything, and you only have to screw up one of 100,000 holes while manufacturing the board for 5 months to scrap it.
yeah, and
Like,
so I think I'm hearing kind of where the entry point is for additive because it's essentially consolidating all of those steps into one deposition slash sintering process that
that's right,
occurs essentially in parallel involving all the materials. And then
right,
you just slowly build up the entire board from, like you said, essentially from nothing. And you eliminate
hmm
all the back and forth and going through the shop multiple times,
right.
and you wind up with a finished product. I think
That's right.
what people would question with that type of process is what's the scalability?
Yeah. So one, we like to say the complexity of boards is free for us.
Yes,
Doesn't matter.
sure,
Okay,
that makes
so
sense.
complexity is free.
Your complexity
So the
is
scalability,
your complexity is limited by resolution.
yes, but so is traditional manufacturing, right?
Okay.
And we're working on getting smaller. Right now we have 75 micron limit, and we changed that in the last half year down from 110, and we'll continue to drive it down. Um, but yeah, it's the complexity is free. But in terms of like where we're going, so the today's product is DragonFly IV.
Hmm.
That is available for purchase today. We have about 70 fielded units, um, and the how do I answer this. our product roadmap, because we didn't get into this, but we have this wonderful fortune of only in COVID this all happened, but our company raised $1.5 billion in the public markets last year. And so we actually have the R&D kind of money, the war chest to make this happen. And I would even argue more than any other company in the world, even the big ones aren't throwing this at this problem. And so now we have product roadmaps that are looking at the next machines, and the next, this is kind of branching here, but we are focused at a PCB production machine that would be PCB, but again, the complexity is for free, and so if you have vias don't go anywhere, it's fine, but it does conceptually think about layers. And then something that's more focused on just pure sexy 3D stuff. But effectively they kind of operate the same. And so we're working on to make sure those throughputs are adequate to what a high mix low volume, and that world is automotive is low volume these days, right? In terms of where the cutoff is. We're not going to be printing smartphones, okay? But I would love it. We can get a huge demand. But the throughputs that we're thinking about are reasonable for what these manufacturers need, not to mention everything else that comes in, everything that comes along with that. So you're asking about speed for delivery, but then we're also looking at how we make sure that the pricing is right, that, again, the complexity is free, the yields are much better, the environmental and sustainability of this process is night and day different, right? IP protection, because you can have the printer in your office, right? I'm putting 6 printers in this wonderful class A, class A regular office. There's not a manufacturing plant behind me, and I'm going to make circuit boards no different than what you order from your OEM.
Yeah, they talk about being in the same office as your manufacturer, taking that to a whole new level.
Yeah. And so you even see, right, when people are ordering boards, or you start to do, oh, here's your first run and how are the yields, and then maybe they're doing it with somebody local, a local shop, just to get it done and get quick returns, fine. And then when they have to go to production, they're going to a company like TTM.
Sure.
And now wait, they got to start it all over again, because you really need to understand your registration and the material movements, and you can wind up scrapping. And it is not a copy and paste between the plants. Even plants within the same company, there's these sort of thumbprints that happen between the plating line chemistries and the humidity and temperature of the entire, even where the plant's located, and all these things add into it. For us, if you print it in your office and you're just doing your prototyping there, and then you want to go to manufacturing in the future, it's the same machine. Sure. It can order. And so we think about distributed manufacturing in that place. And so where you could note, we're kind of going back to what happened to printing, actual desktop printing, right? Gutenberg doing the press and printing presses and all these kind of things. Eventually, what people are more familiar with is this desktop publishing. And just go back a couple decades ago, most of the people listening to this will remember, if you needed a lot printed, you weren't printing it on your office. You were going to Kinko's or a printing house.
I still do that.
And most of that really doesn't. But you can have it on your desktop now, and so you're doing it, and then you're printing it right there. And so we want to be in that place in the conceptual idea where you have this distributed stuff, where you can print anywhere, and then again allows for IP protection, distributed manufacturing, better utilization of all the equipment out there, and so that's the place we're trying to really get to.
Okay, yeah, that's all really interesting, I can definitely appreciate the effort that you guys are putting into, really trying to get this to be more than just prototyping, because I think a lot of the hurdle to much broader adoption of 3D printing as the standard process, not the exception process, is the scalability. How easy is it to parallelize? How easy is it to maintain? The skill level of the operator required. All of these things are a factor. And I think you guys are kind of setting them up and knocking them down one at a time.
Slowly, yeah.
Slowly.
And those things still exist in traditional manufacturing, right? We really had a catalyst event where we were able to generate all this capital to make this happen, right? The company's been around since 2012, and we put $50 million in R&D in those 10 years, and now we can do that almost a quarter, if you will, right? And so we're really accelerating that. But now we're really doing it from an M&A process, because you can sort of buy and integrate. solutions that work so you can shorten the timeline for development. And it's not that we're giving up on all internal R&D. We have 130 scientists right now. By the way, that's double how many employees we had totally last year. So we're really getting that flywheel going. And a lot of it does come down to, especially the next materials, is material science. That is the key, as with most 3D printing.
Yeah, absolutely.
Yeah. So.
So,
Yeah, so I mean, and it's all about prepping the ecosystem for that too, right? Standards. So we could make the best machine since sliced bread, the next product line and it's beaten either throughput. Make these numbers up, right? It's kicking out a circuit board every hour and a half, which is faster than a plating cycle. It'd be faster than a regular plating cycle when it goes through everything, right? All the wash cycles and everything. Let's just assume that's like where we're trying to go or something, right? And so this is like. Um, if that happens, you could release it, and then the industry won't accept it because everybody's nervous about what's the actual reliability and how do we actually think about this in the design. And that's why it's important now that we're really engaging our customers, again, from in academia, but also in industry, in the R&D centers at the OEMs, because they need to learn how to think differently. They don't have to, right? You can do the legacy board you've had forever, fine. But there's so many better ways to do this. Weight reduction, size reduction. That's really so it's important now to start those things. So then as a industry, we can ensure that we have standards that we all feel good about, not start those standards 3 years from now when that machine exists, and then we can all agree on it 3 years from then after that. And so we're trying to make sure those ecosystems get prepped now, to support the adoption of this technology. That's the tall order.
and you say building the ecosystem. I think an important part of the ecosystem for a product or a set of products that you guys are developing is the material sets, right? I mean, obviously, what you guys are doing is totally different from the typical epoxy and glass weave rigid materials, and obviously it's not polyamide, or is it?
Yeah, so I mean, so the machines we have today, DragonFly IV, the output of the DragonFly IV are prototyping boards and proof of concept boards. And again, they're functional, but we need to make sure the long-term reliability is there. So when we have, today's dielectric, you see here, here's a pocket board with a coin battery and a bunch of pockets as well. It's an FR4-like material, right? No glass weave. By the way, you get better DF because of that. But today's material is FR4 like, and the conductive ink is a silver nanoparticle. That is not yet at the conductivity as copper, but there's many cases where that doesn't matter, a lot of cases. But also when you start changing design, particularly in the RF spectrum, one RF generally runs on the surface. But when you don't have to actually you don't have stub issues, you don't have to do 90-degree turns, and you can start to soften those things, even with today's material set and where we're at with our DK and DF and TGs, etc., you can actually get better performance if you design with that in mind. And then you get all the wonderful goodness behind that of, oh, by the way, you can get it tomorrow in your print and iterate faster. So we are working on new material sets, both in-house and through partnerships. We just announced some publicly, if you look at our press releases, that are working on both new dielectrics and new conductive materials, so that our customers have choices of no different than we have choices in regular traditional PCB manufacturing. But you still have to think differently and accept something different. It's almost like, can we get the industry back to build to spec versus build to print?
Yeah, I see what you mean. Like without DFM totally taking over the design.
Right. Now we have our own DFM things we apply, right? Because you can't do everything.
Well, sure, but I mean,
there's still sort of limitations for how close you get things.
Sure,
together.
but I mean, from what you're telling me and from what I know of the product, the constraints are much looser in terms of what you can actually create. Like you could do sideways or writing, or 45-degree vias, let's say, or you could do coaxial lines directly printed instead of kind of like cobbling it together like we would in the PCB, where you've
That's
got
right.
two planes and then a strip line, and then you just line up vias, and like that's your coax line.
Exactly. Exactly. So, I mean, you brought it up there. So there's some LEDs on edge, right? Trying to traditionally manufacture that, you'll lose it in the
Right.
routing process. And then you actually see these components, these resistors and capacitors, not the IC, but the resistors and capacitors there. And if I turn it on end, you don't see them
Hmm.
because
Yeah.
it's embedded. One of the reasons we bought SMTech, by the way. We do this by hand. We stop the print and then add it, and then we go continue again. And so when we have SMTech fully integrated in our future machines, it's about pick and place directly in there, pick and place dispensing,
Yeah, so you,
etc.
you just brought up
Um,
something. Actually, you guys did just acquire a company that does pick and place and a print head company,
mhm.
and so you're really trying to vertically integrate the entire process into a single machine or a set of machines.
That's right. So I would call the acquisition of SMTech is sort of a vertical integration into PCBA, um, but also adding things you can never do before. We're embedding active components inside of the boards, and it's nothing to do that. As we go down, the I don't know if it's as much vertical integration as controlling the deposition method, like you say, which is the print head. Really the engineering behind that is mainly driven by the print industry, color printing, and people in 3D printing have been using these things and different adjusting their viscosities to and whatnot to get through it. And so now we're able to control sort of where the science meets the engineering, right at that head of the print head there, and the controller in order to drive it for our purposes while still satisfying the customers that we already have from GIS in the traditional print industry. And so you'll see our sort of what may look like as we go through our M&A activities, a holding company, but it's like the most strategic, beautiful thing I've ever seen is we're not a holding company. We're buying these things and still operating those product lines, which is great because we need more revenue and things like that. But we're doing it strategically because there's something that we can integrate into the electronics printer. I'm going to call it AME printer, additive like manufactured electronics, but to be all encompassing of the future ones. And also what technologies we've put into that, in particular DeepCube, to apply to other things. And DeepCube is our machine learning company. Because to really, really do this well, we're not going to be able to program every single layer and how you understand different structures, right? And so there's this artificial intelligence, the robotic brain that gives the feedback loop to making each layer and adjusting and sort of like having a real-time AOI on every single layer, though it's more than just AOI. So you have sort of closed loop process feedback um,
So
as you
I
build
have
it.
a quick question about that. So this isn't the typical approach with 3D printing where you're basically like generating STL files, send them off to a printer, click a button, and then it goes. Right? This is
No, it is. I mean, we can do Gerber direct or
okay.
STL, but um, it is. But during the process is ensuring that we have that closed loop system where we can adjust things that we're
Oh, so it's
seeing, and then
adjusting
it starts
it's
teaching
adjusting the
itself.
parameters as it prints to ensure that you get the yield, or you
The,
get the quality.
yeah. No, that's where we're
I
trying to
see.
go with it because that is how you really um, drive the things that you can't again program because you're never going to figure out how to do every single different structure that the creative engineers will try to do. And you kind of you discussed it here, right? When you start talking about impedance matching and shielding and all these things, effectively the industry's kind of tricked it out in a 2D sense and play all these hacky things of ground planes and all these kind of stuff. But we don't have to do that. If you need coaxial shielding, print a coaxial cable down the
Right.
middle of the board. I have one. I don't have it with me. Um, or here's one, and again I don't have it set up fully, but this is a low pass
Hmm.
filter RF with all passive components built into it because we can put capacitors in between there and there. Even this sort of thin board, right? It's a thin
Yeah.
board. It's a very thin board. There's those capacitors that you see, the four squares. There's 55 layer capacitors in traditional sense, 55 layer. In that, like you can even get traditional laminates that small, even if you wanted to pay for capacitance for those laminates. Um, and so we can just do it differently, and we can embed it in there, and you get much closer on for passive components to ideal than what you can actually get. I showed you the capacitor, but I have plenty of other examples. Could have one here, but coils, right? Everybody's coil board, right? Round the circle through a via, round the circle through the via, right? And for us, we can do a continuous spiral. Now, in order to actually design that, you have to get into a maybe from ECAD into MCAD to actually add that feature. But that's what we do. So we really get much closer and remove the parasitic effects of what the industry is used to.
So in terms of, the integration with the assembly process, and then integration with like the as you put it, the AI that kind of helps run the entire process. You also brought up total product 3D printing. I mean, do you envision a day where you basically have like one machine and you just click the button on the computer and it spits out your iPhone? It just prints it right there. Is that just too far?
I think no, I mean that's our mission is to make this Industry 4.0, one-click distributed manufacturing. We were at IPC Apex, and I was FaceTiming my kids, daddy's here kind of thing, and I was showing them around the show, and they get to see all the cool machines and all that kind of stuff. And it actually hit me as I described to them. I was like, what my company's trying to do is take every single machine you see in this entire conference hall, put it in the size of 2 refrigerators. All of it. It's like the penultimate lean process. Now, again, we don't purport, by the way, that we're going to make every single circuit board in the world. I also want to ensure that competition actually comes. What we're doing is very altruistic, like especially from an environmental sustainability point of view. When we say AME, that's not Nano Dimension's AME. It just so happens we're the only ones to do it, but we need AME to come to the world, because do we really need to mine all this copper just to remove 95, 97% of it on every single signal layer? Like, it's crazy, right? Even the industry has the term etch off. What is etch off? Take your laminate, it already has copper on it, and etch the entire copper piece off, because I actually don't want copper on that layer. I just need a thicker laminate. And so we've done it this way since 1958, and we just haven't had catalyst events. I would say the only things we really added fundamentally are lasers. The lasers are still doing.
It's still subtractive.
Just an imaging process. It's an imaging process, and then we do vias with it, and then there's a bunch of reliability issues now with stack micro vias, and so and then more plating cycles and just more processing, but nothing fun. Aside from that, it's these PCB plants have all these different processes, and what's the process engineering there? It's like I'm going to go to this machine A, and then B, and then C, and then the next board is I need to go B to C to A, but it's the same machines. It's not fundamentally different. And so when you focus, in from a lean manufacturing concept, when I was running circuit board shop, you sit like in front of the machine. How do we do this better? How do we do this better? And that usually lean process, how do I get the process upstream and the process downstream to kind of come together? And we did some design of new equipment and got lean in. At least we were the 800-pound gorilla at TTM, where I could get OEM equipment manufacturers PCB production to lean in a little bit and say, okay, let's go there and develop this. And so I leaned it a little bit. This is
this is on steroids, right?
Especially with SM Tech.
Yeah,
exactly. And it is absolutely bold vision. But it's got to start somewhere,
well,
right?
You got to have a bold vision to get anywhere, I guess. I mean, that's totally fair.
So yes, we do want to print these things, this fully assembled board out the back from thin air.
So
and I'd love it if it was this drone fully assembled with a battery and you could fly it out of the machine.
Yeah, absolutely. Yeah.
Why not?
Well, and then print the battery, right?
Yeah, which there's battery printing technology on that. We're not there yet. And again, with today's machines, just to be clear for everybody on the podcast, prints are prototyping and proof of concept boards. And everything we're talking about here is sort of grand visions of maybe how we try to get to the future. But,
so people that know me know I'm a physics and materials guy. So I definitely want to ask you some questions about the possible future material sets. So given that you're able to basically, I don't want to say print anything, but potentially engineer materials, different types of materials that could be printable, what other material sets do you see besides just insulating dielectric and then conductors? Do we have semiconductors on the horizon? Do we have transparent materials on the horizon? Do we have transparent, flexible
Right.
materials on the horizon?
Um, so since we're a public company, I can't discuss everything fully, and so we'll say this does not reflect the opinions of the company. Um, eh, I think one, there's you've got to have new metals, and and everybody wants to say, oh, you need copper because we use silver. I mean, technically, silver in bulk is better than copper. It's expensive. However, we're only putting down what you need, so it's a little different than what you're trying to do when you mine everything and then remove it all. Um, and we have to have other metals in order to actually get passive resistors the way you want them, or maybe there's other ways to check it out. But there's also reasons to have different approaches to metals. Not all metals are going to probably be able to fit through an inkhead, but we're going to try. We really believe inkhead technology is what we need to do to get to the throughput we really need. But there's other deposition methods, and I think we're not adverse to that as we talk with other companies. Um, and so, we have a sort of a CI or conductive ink
Hmm.
line of attack. Um, but even, again, at that, talk somebody at IPC grab me like, oh, it's silver now. My customer needs copper, and not even getting into like what we're working on or why it's this and what we're working on copper, etc. That's the mentality, right? Is I only want to understand it because my customer needs
Well, do
copper.
they really need copper?
Uh,
Yeah.
do they really though?
Or do they just need a conductor?
um, I mean, maybe they're doing something that has to be, that element, and
But if it's
I
if
don't
it's
know.
just a
That is that is an
yeah,
entry
well, if it's just a
mentality.
rigid board and it's just carrying a signal, you're right. It doesn't need to be copper. And if it just needed to be copper, we wouldn't plate up or we wouldn't apply surface finishes to a finished board, right?
Exactly.
Because I mean, once you
Right. Yes, which is, there's certainly difficulty, by the way, of trying to deposit copper with air around it, and it's oxidizing, and you're going on, and you have to get the next layer fast. Like those are the
right,
things we have to
right.
struggle with. But yes,
Well, and
exactly.
I mean, once you take into account the skin effect, I mean, the signal isn't even in the copper anymore, anyways. So why do you care if it's copper or
No,
silver or gold
and
or
what
anything else?
totally. And what's the best conductor, anyways? Um, so and that's the mindset. But in terms of dielectrics, right? Again, we have an FR4 like material. We have no glass in it, so we have to think about different ways to strengthen. But redesign also gets you there. We have people designing PLLs that are this big and then making them 3D Q PLLs with active components embedded, and now you're getting down to that size. There's some examples on our website. Um, Different form factor. Why do people need flex everywhere? Well, there's uses for flex, but there's a lot more flex now because of the connectorization, because the form factors you're trying to put it in where you shove it in there. Well, if you're actually you can design the board in any shape you need. Do you actually need flex?
That's a fair question.
Um, and again, I'm not being over generalized, but there are reasons people go into flexes for those kind of reasons. And even at that, if we print, even with today's material, we print it thin, you can bend it. We're not doing flexible
Well, then there's also like
electronics, but
foldable
um,
for flex, right? But I'm sure at some point, yeah,
yeah, it's one time. So why not just print the
yeah,
size you need, and make those connections that you need, or um, and so on the dielectric front, we're working on different things that to strengthen it, but also better TGs. We have a low temperature reflow process right now with today's material, but it works and assembles. Um, and then certainly in the RF spectrum, getting better DF materials. But even at that, I think, my opinion, people are going to argue with me about this too. Like everyone goes, oh, you need Rogers, Rogers, Rogers. One, really, really expensive. But oftentimes, when you really get down to it, it's way over designed half the time. And there are a bunch of good competitors out there, and not to poo-poo Rogers, but like that's where everybody, because it's got this name recognition, that's what you need. And so if we don't have Rogers printable material, by the way, Rogers just announced last week they're going into 3D
hmm
printing and printing it, so they're coming along too. You don't have to. You need the thing that operates for what you need. And for us, especially to start mixing different dielectrics in the future, if you only need RF on this portion, then just use the
sure.
RF over there, and then use a different dielectric here, and you get your material costs down because and worse today, it's the entire layer one, layer two have to be whatever RF du jour you have, and so you make sure the materials you're ordering are what you really need versus what you're comfortable with, and I think that's just some of the bleed in uncomfortableness of engineers to really want to go. We've always used this material, so if we change it, even on a cost per, I don't have to requalify it, right? We've really gotten in our own way for being creative and evolving. You know what I'm saying? Like even when you change manufacturers, you have to requalify it and all this kind of stuff, but it's the same thing at the end of the day. And so as we're coming along here, we have to be able to design and iterate really fast, a la IPC 1958, right? But now it's so locked in, and for right reasons. Don't get me wrong, okay? Because especially in the low mix, high volume, sorry, the high mix, low volume world, most of the things you're doing will probably kill people if you don't get it right. Um, and so there's the right things to do, but you really need to come back to what's the essence, what's the reason that you're doing those things, and have those engineers come on this journey with you and disrupt. And then people will get comfortable with it in time, and we'll do the right things, and we'll work as an industry to try to get these things into the correct standards or match the slash sheet to the best of our ability, and realize that, again, it's sort of build to spec versus built to
Yeah.
print.
Well, I think we're going to have to leave it there and just note that the future looks bright for Nano Dimension, and it's great to see how far you guys have come. I remember meeting some guys from Nano Dimension a couple years ago, and you know, I could tell they wanted to get to this point where you're at now, and it's great to see that you guys have been so successful, and I wish you all the continued success that you guys deserve.
Great. Appreciate your time as well.
Absolutely. Thank you so much for coming on to the OnTrack podcast. And for all of the viewers and listeners out there, just remember, don't stop learning and stay on track, and go check out some of the links we have in the show notes. Go check out the Nano Dimension website and learn more about this very interesting technology. Sean, thank you so much for joining us.